Assalamu alaikum. Welcome to our video demonstration for the complex engineering problem of EEE 4705 microcontroller based system design. I am Mahir Fayaz Anan presenting on behalf of our group section B group 1. We have designed a standalone handheld tic-tac-toe gaming device for Retrologic, a startup focused on retro gaming products. The challenge was to build a fully functional game on the 89C51 microcontroller programmed entirely in 8051 assembly language. No high-level libraries, just registers, ports, and logic. Our device supports two modes, player versus player, where two people play on the same device, and player versus AI, where player competes against a rule-based AI opponent. The game is displayed on a 16 by 4 character LCD and controlled through a 4 by 3 matrix keypad. The complete design, including the hardware, schematic, assembly source code, bill of materials with Bangladeshi market price, and power consumption analysis, is documented in our technical report. Now let's begin. Our first task was to select the input and output units. For the input, we evaluated four options: a 4 by 3 matrix keypad, individual push buttons, capacitive touch keys, and a joystick. We selected the 4 by 3 matrix keypad. The keypad has pre-labeled keys 1 through 9 that map directly to the 9 cells of the tic-tac-toe grid. It requires only 7 input-output pins through row-column multiplexing, compared to 9 or more individual pins for discrete buttons. While the capacitive touch panels requires I2C driver ICs, which ICs gonna cost a lot and much software complexity. A joystick provides port usability for selecting individual cells in a grid, while the 4 by 3 keypad was the clear winner in all three categories: usability, cost, and I/O efficiency. For the output unit, we compared the 16 by 4 character LCD, 7 segment displays, and LED matrix. We selected the LM041L, which is a 16 character by 4 row alphanumeric LCD. The 16 by 4 LCD can display the full 3 by 3 game board with separators, player next turn, and status messages like X wins or draw, all at the same time. 7 segment displays cannot show alphabetic text at all. And LED matrix needs 16 or more driver pins and a complex scanning routine. Here is our complete hardware schematic in Proteus. The central component is at 89C51 microcontroller, a 40-pin DIP package with 4 kilobytes of 1-chip flash and 128 bytes of internal RAM. For the clock circuit and 11.0592 microhertz crystal is connected between XTEL1 and XTEL2 with 233 picofarad load capacitors C1 and C2 to ground. We choose 11.0592 megahertz because it generates without error, which is useful for future expansion. The research circuit uses resistor R1, which is 10 kilo ohm, and capacitor C3, which is 10 microfarads. At power on, The capacitor keeps the step in high for approximately 100 milliseconds for the microcontroller begins execution from address 0000. The LCD is connected in 4-bit mode. The data lines D4 through D7 connects to port 1 pins P1.0 through pin 1.3. The RS pin connects to P1.4. The RW pin connects to P1.5 and the enable pin connects to P1.6. The VE pin connects to a potentiometer RV1 for contrast adjustment. The 4x3 keypad connects to port 3. Row lines connect to P3.4 through P3.7 as outputs. Column lines connects to P3.0 through P3.2 as inputs with internal pull-ups. The scanning routine drives one row low at a time and reads which column goes low to identify the key pressed continuously. Pin 31, which is EA, is tied high to use internal program memory. Unused port pins are available for future expansion such as buzzer or EEPROM. This is our complete hardware overview. And now let's look at the software. So here you can see the machine flowchart, and our software is written entirely in 8051 assembly and structured as a finite state machine with modular subroutines. The game board is stored in internal RAM addresses 30H through 38H, 9 bytes, 1 per cell. 0 means empty, 1 represents X and 2 represents 0. The game flows through these states: startup, mode select, game initialization, player turn, validate moves, update board, check win, check draw, AI turn if player versus AI mode is active. On power up, the welcome screen appears. The player presses asterisk for player versus player or hash for player versus AI. The keypad then scanning the subroutine drives one row low at a time and reads the 4 column inputs. When a column reads low, we compute the key identity and apply a 20 millisecond software debounce delay before registering the key press. Win detection checks all 8 winning combinations stored in a lookup table in code memory, 3 rows, 3 columns, and 2 diagonals. Each entry has 3 board indices. The movec instruction retrieves each index from the flash and compares the 3 board cells. If all 3 match a non-empty player value, the player wins. For the AI algorithm, we use a rule-based priority strategy that guarantees the AI will never lose. The AI checks 5 priorities in order. First, win. If the AI has 2 in a row with the third cell empty, it takes that cell immediately. Second, block. If the human has 2 in a row with the third empty, the AI blocks that cell. Third, center. If the center cell is empty, the AI takes it. Fourth, corners. The AI plays the first available corner. Fifth, edges. If no corners are available, the AI plays an edge. This approach uses the existing win table lookup and simple sequential checks. No recursive minimax tree is needed, which keeps us within the 128-byte RAM constraint. The AI executes in 100 microseconds, making it insusceptible to the user. Now, let us see the simulation. Now, the simulation is now running. Uh, you can see the LCD showing the startup screen with the game title and the mode selection prompt. Now we are going to press asterisk for select player versus player mode. The display updates to show the empty port and player external. Now let's play one game. X wins. The LCD displays X wins. Now we press hash to enter player versus AI mode. Player X is the human and player O is our role-based AI. Here you can see the AI is blocking my moves perfectly and it is reading the game correctly. Here the AI identifies it can win immediately by completing a line. In our AI, it never misses a winning opportunity. That is priority 1 in our system. So that let's try to draw. For this we are going to use that famous trick, as it lets me to give the first move. I am going to take the center. Draw confirmed. The AI plays optimally throughout and was not beaten. In conclusion, we have successfully designed and simulated a fully functional standalone handheld tic-tac-toe gaming device on a at 89C51 microcontroller in 8051 assembly language. The system meets all requirements of the CEP brief. We implemented player versus player and player versus AI modes, a rule-based AI that cannot be beaten. So we tried to give a draw, and we get a clear visual feedback for all game states and all required supporting hardware within a prototype budget of about 350 to 360 taka. The current limitations of our system are no persistent score storage due to the lack of EEPROM on the 8051, a single fixed AI difficulty level, and no audio feedback without a buzzer. For future improvements, we propose integrating a EEPROM for score storage, adding a passive buzzer for audio feedback, and implementing multiple difficulty levels for the AI. and potentially migrating to a more capable microcontroller for graphical display and Minimax AI support. Thank you for watching. The complete source code, schematic, and technical report are submitted to the Google Classroom. Assalamu alaikum.